Dear all, I am Malati from SR University. Today's video lecture is on design for interfacing read-only memory and random access memory. Now we have to interface 4 kilobyte EEPROM, erasable programmable read-only memory using 2 kilobyte EEPROM because 2 kilobyte EEPROM is available in the market, not 4 kilobyte. But for our task, we need to have 4 kilobyte. So what we should do? 2 kilobyte EEPROM, 2 we have to take, 2 in numbers we have to take and then connect them and then connect to the 8051 microcontroller through interfacing. So this is what the method to use 4 kilobyte. If you want to have 4 kilobyte, then we have to use like this. And then normally we are telling read-only memory, random access memory. But in read-only memory, not ROM directly. So it is available in the varieties only. So out of those, we are taking EEPROM. So EEPROM is coming under the read-only memory. So for memory interfacing, 4 lines must be interfaced. So we require 4 lines and then 2 chips needed. So that I have already told you. So what are the 4 lines? Address lines, data lines, control lines and chip select. So these 4 lines are already available in the 8051 pin architecture. For ROM, address lines for 2 kilobyte equal to 2 power 11. So 2 power 11. So depending on the capacity, 2 power 11. These many number of locations we can have. So for this to address them, 11 lines are needed. And data lines 8. That we know 8051 data handling capacity is 8 bit. That is why data lines are equal to 8. And then control lines. It is memory read. So it is made possible by using PSEN bar, programmable status enable of 8051 is connected to read-only memory. And how the 11 lines are used, that I will tell you in the design. So normally basic architecture for using the read-only memory is coming under 2 types. First one, internally built ROM is available, the internal ROM. And for extension, we can use external read-only memory. And under which condition we can use internal as well as external. First one, for that EA bar pin is available. Enable access. So what is enable access? Enable access, okay, by the name itself we can understand the meaning. Enabling the usage of external read-only memory, that is EA bar. Okay, it is low signal activating. And then if it is grounded, that means EA bar is equal to 0, then it is possible to use external program memory of 64 kilobyte. So the total capacity of external program memory is 64 kilobyte. Totally we can use solely without using the internal program memory. So the address starts from 0000 to FFFH. And this FFFH also I will tell you in the designing how the address is coming like this. Starting okay, no problem, it is 0000 only. But the ending FFFH, how it is coming, I will tell you in the designing. And then when it is equal to 1, A bar equal to 1 means it should be connected to, vice versa. It is 0 ground and it is VCC. So VCC equal to 5 volt. It is connected to the EA bar. And then in this case, we can use both internal memory as well as external memory. But when EA bar equal to 0, only thing we can use external ROM only. Okay, so here it is. Now, internal memory is 4 kilobyte capacity only. We cannot change. It is already available in the 8051 microcontroller. External memory, it is 64 kilobyte available. But when we see here is 64 kilobyte available, but we cannot use 0 to this value 4 kilobyte value we cannot use in the external memory. Why? Because these addresses, I mean starting from 0000H to 0FFH, so these memory addresses will get repeated. That is why we should avoid using this 0 to 4 kilobyte in the external ROM, because internal ROM 0 to 4 kilobyte only. This we should use whenever it is equal to 5 volts. I mean EA bar equal to 1. So we cannot avoid, we should use. So both should be used. So internal it is fixed 00002 0FFF, and since we need to avoid the coincidence of these addresses both in internal as well as external, we are starting from 1000H to FFH. So this is the next address is 0F1 and F next to F 0, next to F 0, next to F 0. So finally ending address is FFH only, as we have seen in this diagram. Next one. So now coming to the address, how to frame the address location, how to mention. So we know 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 up to 2 power 11, because we are using 2 kilobyte and 4 kilobyte only. That is why I am writing up to 2 power 11 only. And here the values are 2 power 0, 1, 2 power 1, 2. So 4, 8, 16, 2 power 5 is 32, 2 power 6, 64, 2 power 7, 128, 2 power 8, 256, 2 power 9, 5, 12, 2 power 10, 1024, and 2 power 11 is 2048. Now, we need to have 2 kilobyte. So add these locations 1 plus 2 plus 4 plus up to 1024, we will get 2047. And in microcontroller, we have to mention it as 2K. So 2K means 2047. It is not 2000. So 2047 is equal to 2 kilobyte. And how many address lines here? See, start counting from 0. So we have to number it as 1, 2, 3, 4, 5, 6 up to 11. So it is not 11. It is not 10, because starting from 0. So totally it is 11 lines. 11 lines for address. And if you put 1 for all, then it is these 4. If you put 1 1 1 1 means F, and these 4 1 means F, and then here it is 1 here it is 0, nothing is there means 0, so 0 1 1 1, it is equivalent is 7, therefore 0 7 FF. So we can blindly say that 2k it is equal to 0 7 FFH. And then suppose if you add, so up to this only I have added. So 2 power 11 equal to 2048. If you add 2048 and 2047, it is equal to 4095. So 4095 is equal to, in microcontroller it is 4004 kilobyte. So 4K. But to represent 4K, all the bits are equal to 1. So then only you will get the 4 kilobyte capacity. So if all are 1, as I have explained previously, it is F, it is F, it is F. So 0, F, F, F. That is why in the previous diagram for 2 kilobyte I have mentioned the address 0, F, F, F. So it is 4 kilobyte equal to 0, F, F, H. In the external program memory, I have mentioned the starting address 0000 up to 0, F, F. Now, internal ROM. So that is what in the previous slide I told 0000 to 0 FF. It is for 4 kilobyte. How the address is going on. So we have to start from this address and end at this address. Now external ROM. We know that it is 60K. So next address is in the external ROM, we are not using this 4 kilobyte once if EA equal to 1, and at the situation we need to use both internal as well as external. That is why we are avoiding these two these locations. The next address is from 0 1 for F next is 0, F next is 0, F next is 0. So starting from this address 1000. Next once again ending address is FF that we know. Ending address 64 kilobyte ending address is FF. And then interface 8 kilobyte RAM. So as usual, so in the ROM 4K available, but 4K we are going to design. So using 2 kilo. In the same way, for 8 kilobyte RAM, in the market 4 kilobyte RAM is available. So we need to use two number of chips of 4 kilobyte RAM in series, and both are connected in series, and it is connected to the 8051 for interfacing. So finally we will get 8 kilobyte RAM. So here two chips are needed. So I told you already. And then address lines, it is for 4 kilobyte. It is equal to 2 power 12. In the previous slide I have shown you starting from 2 power 0 up to 2 power 11. So if you count from 0, it is not 11. So 12 address lines are used to represent this 4 kilobyte ROM. And data lines, it will not change because 8051 each capacity is 8-bit handling only. So for data, 8-bit line, 8 lines only. And then for control, so in case of ROM, memory read, because read only memory, we cannot edit. Only then what is the content available inside can be taken. That is why memory read in the previous case. But for RAM, we can able to write as well. Not only read, write as well. That is why read bar, write bar. It is memory, right? For RAM in 8051 microcontroller. And next one, for RAM chip, no need to have any confusion. It is easy only. So when it is 0, full external memory. So external memory 64 kilobyte. Address is starting from 0000H to ending FFH. That's all. So if it is 1 means only both will be used, internal as well as external. And then coming to the designing. So starting EEPROM, external ROM, starting location is 1000. So I have already told in the previous slide, because 4 kilobyte ends at 0 FFF. That is why next address is 1000. So how will you mention this one? Here I have written A0 up to A15. So 1 means 0, 0, 0, 1. So these four combinations are 1. And then 000 means all 0, all 40 and all 40. And it ends in 2 kilobyte. It should cover 2 kilobyte. And what is the value? 07FF for 2 kilobyte. I have explained in the previous slide. So 1 is 1 only, 7FF. That is the 2 kilobyte capacity. So 1 means 0001, that is same. And then 7 means 0, 1, 1, 1. F means 1, 1, 1, 1. Again F means 1, 1, 1, 1. This is for EEPROM 1. And the next EEPROM 2 in series. So what is the next address? 1, 7, next for next number for 7, 8. Next number for F 0. Next number for F 0. And then we need to write the equivalent. 1 means 0, 0, 0, 1. 8 means 1, 000. This is 8. And then 0. So all zeros. This is all 0. Okay. Now from this address, 2 kilobyte capacity should be covered. And for 2 kilobyte, what is the value? It is 7FF. In the previous slide, I have explained. So, if you add from the starting address 1800 by 7FF, what you will get? F plus 0F, F plus 0F. 8 plus 7, 15. 15 equivalent is F. And then F is carried over as it is. So next, RAM address. RAM, it is very easy. Starting address is 0000 only. So all zeros we have written. And then 2 kilobyte. We know that 0FFF. So 0000 and F, 1F, 2F, 3F. Next one. Next starting address. What is starting address? After completing 2 kilobyte, next to 0, 1. Next to F, 0. Next to F, 0. Next to F, 0. So 1, F, 1, 0, 0, 0. This is the address, starting address of the second RAM. And ending address. Once again we have to add with FFF. So initially it is starting address is 1, 1, 0, 0, 0. Next it is 0001. Next, F means 1111. Next F1111. Next F1111. That's all. So in this case, we need to, in the previous slide, we have talked about the chip select. So what is chip select? That chip select, either it will be 0 or 1. That value will be taken from this designing itself. Now consider this, for EEPROM 11 lines are used. 11 means 0 to 10. 0 to 10. So this will not be used because same. Consider this one, it is 0, it is 1. So chip select is taken from 0 to EEPROM 1. And chip select is 1 taken from this for EEPROM 2. In the same way, for RAM, 12 lines will be needed. So after 12, it is 0 to 11. And then this one is, these are all 00 not used. If you take this 00, so select is 0 for RAM 1. And then select is 1 for RAM 2. So in this way, select value will be taken from this address lines itself, because unused lines will be used for making use of chip select. And then external ROM starting address. So whatever I have written, orally I told in the previous slide, that is written here, 1000 starting address. For 2 kilobyte we need 11 lines, therefore 17FF, that 2 kilobyte 7FF I told you. And next 2 kilobyte starting address is 0, 8, 0, 1800. 11 lines. So 11 lines means 2 kilobyte, it is equal to 7FF. So 1, 8 plus 7 F plus 0 F, F plus 0 F. That also I have already explained. And red color chip select 0, 1. All for ROM, A11 for ROM, A11. 11th address is used as chip select. And for RAM, A12, 12th address line is used as chip select. And CS bar to select in multiple devices. OE bar, it is output enable. So for read-only memory, it will give out the data. So for taking the data, for reading the data, this OE bar should be enabled. It is in ROM and RAM, it controls the flow of data from the chip output pins. In ROM, OE bar must be active to enable data out, and in RAM, OE bar separate WE write enable read write pins also needed for write operation, because in RAM both read and write operations should be performed. And then, so for read operation, select important, we are taking from the address line. And OE bar is important because then only the outputted data will be read. And it is write enable. It is, these three should be active. And then write, for write operation, select is common for all, either RAM or ROM, both needs select pin. And then write enable, it should be active. And then strobe signal, it is one more signal available in the latch that I will explain in the next slide. And ALE address latch enable, both from 8051 are connected to control data latched or stored by the latch. And what is the name of the latch? That pin number I will tell in the next diagram. To latch lower 8-bit address, the latch is used to store the lower bit address. EA, external access, already I told you. It enables external ROM 64 kilobyte when it is 0. When it is 1, internal 4K, and in addition to external 60K will be used. So this is the diagram. It is 8051 and it is 40 pin. Okay. What are the pins utilized for the read-write operation? I mean, for interfacing RAM and ROM, we have that particular pins only taken into account. So in the port to 8 to 15 address line, it is upper byte address line. It is separated. In case of lower byte only, either address or data, it will become as confusion. So, if we use latch, this latch will be used to store the lower byte address. In this way, address will be separated from the data so that both cannot mix at any time. So here 8-bit latch 74LS373, it is that chip, and this STB pin, I mean strobe pin, is connected to the ALE, okay, address latch enabled pin of the 8051. And then AD0 to AD7, which is from the port 0, multiplexed address and data starting from 0 to 7. These 8 lines are connected to the 8-bit latch. See the direction. It is say unidirection, but address as well as data means bidirectional. So data means definitely bidirectional, so to and fro. And then so after given to the 8-bit latch, it will separate very nicely A0 to A7. Separates the address from the data lines. 8-bit 8 lower byte address will be separated from the 8-bit data. So data will be separately coming in the line, and then P send bar from the 8051 needed, and read bar, write bar, EA bar. So all are connected to how they are connected to the RAM and ROM. It is seen in the next slide. See, first one ROM, EEPROM 1, 2, each having 2 kilobyte capacity. OE bar definitely we needed for ROM, and then chip select is also needed. So OE bar is it is connected from the piece and bar of the 8051, and CS bar equal to 0. And if it is inverted, then 1, that 1 is given to the second ROM. So that is what we have seen in the design table. 0, 0, 2 zeros will be there, 1 0 will be taken out. In the same way, 1 1, 2 ones will be there, 1 will be taken for the chip select. And then here also, A8 to A 15, and then it is D7 to D0 data. So here it is D7 to D0 data. And here it is A11. 11th address line will be used for chip select. Next one, RAM. How two RAMs are connected? RAM 1, it is 4 kilobyte. Similarly, chip select bar. This pin is taken from the A12, 12th address line 0. And for second RAM, it is 1, so that it is inverted and it is given to the same CS bar pin. RAM 2 is also 4 kilobyte, RAM 1 4 kilobyte. So here the address line is A11 to A0. And then D0 to D7 data, it is bidirectional. So here A0 to 11, in the previous slide A0 to A12. And here A11 to A0, same thing, D7 to D0 bidirectional, and only thing, read bar is connected to the OE bar. Output enable should be enabled. Then only the data will be read. And write bar from the 8051 microcontroller, it is connected to the WE bar of the RAM chip, write enable bar. So here also read bar from controller, Y bar of RAM, write bar of controller, and write enable bar of RAM 2. So with this we conclude. Thank you all.